So I chose to do research with Rex. We actually had the option to choose any supervisor for any kind of research that we wanted to. This was very, very nice. And you had to be a bit careful because it could determine the rest of your career. But I chose Rex because, well, for many reasons, but mainly because I detected a kindred spirit there. We had the same basic philosophy, which is stated actually in one sentence: avoid wet chemistry like the plague. Now, this is actually a typical chemistry lab at Oxford. You don't bring a 2-ton magnet into this environment. It's just not done in those days. We're talking about the the early 1950s. And Rex said he was going to do just that. And to do that, it's a question of doing it all yourself. You have to build all your own equipment. And Rex actually drove one of these old London taxis, which had this space here for very large pieces of luggage. It's actually reinforced to take heavy weights. And he took these 4 enormous chunks of iron by taxi up to the local car manufacturers to have them machined one at a time, and then brought them back one at a time and assembled them to make a magnet. So I want to show you the result. In 1956, this was the magnet that Rex had built. He wound the coils himself. That was 9 miles of wire. He built the power supplies for the magnet with the help of some previous students. And my job was to build the electronics, which you see on the right here. And I won't bore you with the details of that, except to say that the thing that really mattered was this pound spectrometer in the middle here. Now, nobody ever talks about pound spectrometers anymore, but in the 50s, this was the latest thing. This was the best you could do, was to build a pound spectrometer to do NMR. And I'd like to explain why that is, because it's a very simple device. It's a tuned circuit with an amplifier. And then you have positive feedback, and you get an oscillator. The posh word for positive feedback is regeneration. So this is called an oscillating detector. I think the Germans call it an autodyne detector, a regenerative oscillator, but we all call it a pound box. The cute thing about this is that a very small NMR signal in the coil is enormously amplified by this regeneration, so you don't need lots of amplifiers, RF amplifiers, broadband stuff like that. And the other cute thing is you can drive the capacitor with a motor drive and a reduction gear, and you can search for unknown resonances. Now, in this kind of work, you're looking at the radio frequency spectrum, which is just empty, except for just a few blips, which were the signals of NMR nuclei. So an automatic search was the thing you absolutely needed. Now, I'd just like to do a diversion here, a digression, because, and jump forward a year, because I was lucky to go and do a postdoc with Anatole Abragam's group, an incredible intellect in NMR, probably the smartest man in magnetic resonance ever. He unfortunately died quite recently. And so I was in his group at Saint-Clair, just south of Paris, and I'd only been there a few days when a sabbatical visitor came from Harvard by the name of Robert Pound. Now, Robert took me under his wing and we said, let's build a high-resolution machine. We've got nothing better to do. Because he had some really cute new ideas about how to do this. And the new idea is a tuned circuit and an amplifier. And then you turn up the feedback So you have super regeneration. So the different oscillator starts, it goes very fast up to a very high level, which you can't allow to do, so you have to quench this with pulses. In other words, the amplifier is off until you allow it to oscillate, and then noise triggers off an enormous oscillation, and then you switch off again and quench it. So it's a pulsed oscillator. It's wideband because it's very noisy, and it's very easy to find responses because of that method. And Bob had used this at Harvard as a radar detector. Simply put an antenna on it, send out a signal, and if you get a signal back from an airplane, that signal then triggers off the next oscillation. So it's very, very easy to detect very weak radar signals. And if you sweep the quench frequency, then you know how far the aircraft is away because of the delay. And Bob's idea was to say, why don't we do this in NMR? So again, this is a broadband noisy oscillator, but if there's an NMR signal, that signal triggers off the oscillations. And those oscillations become coherent with the NMR signal. If the NMR signal should drift for any reason, the frequency of the oscillator drifts with it. So this is a field frequency control device, and it follows the magnetic field with an error of only 1 part in 200. We tested this by running the spectrum of acetaldehyde. Now, if you read the textbooks, people never do look at acetaldehyde by sweep methods anymore, but if you look at the textbooks, you'll find that all these signals have enormous wiggles on the trailing edge because you can't sweep slowly enough to get rid of them. So this is testing the stability of the machine by sweeping at only 1/10 of a hertz per second through the spectrum. So that's the digression. Now we come back to the Oxford magnet in all its glory. There are lots of things wrong with this machine, but there are two major problems with it. The first of them is that the stability and homogeneity are too poor to do high-resolution proton NMR. And this was brought home to us because we had an American visitor who shall be nameless, and Rex showed him the magnet and said, "Oh, yes, we're doing fluorine shifts." And the American said, "Jesus, I didn't realize fluorine shifts were that big." The second problem is that this was in a chemistry department, so we had at some point to do some chemistry. And so we looked at these nuclear spin systems, of which, best to say, very little except possibly cobalt. Because at that time, Norman Ramsey had a theory of chemical shifts. Now, you have to treat an atom in a very strong magnetic field, which distorts the motion of all the electrons. In order to do the calculation, you need all the excited electronic states of the atom and all their wave functions, and these you don't have. So, although it's a beautiful theory, it's not so easy to apply. But there's one special case, and that if there's one very low-lying electronic state of the system, and this actually happens in cobalt. There's a low-lying state with a splitting of delta, which is actually called the ligand field splitting to those who know these things. And in that situation, the NMR signal is proportional to the inverse of this frequency. So the NMR signal should be related to the color of the cobalt complexes measured by their UV visible spectrum. So you have a frequency of NMR should be related to a wavelength of a UV visible absorption. So if you measure a range of cobalt complexes, you should have a straight line. This is the holy grail of the physical chemist, is to get some kind of straight line plot, and we did. We were happy about that. Note the chemical shift range of cobalt is 13,000 parts per million. It's an enormous chemical shift range, and that's because of this effect. And also the temperature dependencies follow the theory okay. So I have to admit, in retrospect, I'm a bit ashamed of it. We were very pleased of these results. And let me just warn you, if this happens to you and you have a good result, there's one thing to say: watch out. Watch out, because someone else is working somewhere else in the world, and they're going to upstage you whatever happens. In this case, it was two young guys in California, just a few years older than me at the time, Jim Arnold and Wes Anderson. Now, if you get people who are working with you and are just starting NMR, they should be forced to read these two papers. Now, the received wisdom is that high resolution started with the 3 lines of ethanol, the Arnold, Darmati, and Packard paper, and that's true, and that's in all the textbooks, and I don't argue with that. But these two young men took this far further than that. They found all the fine structure in the ethanol spectrum. They discovered chemical exchange. They did strong coupling effects and showed how to calculate them. They did so much more than the 3 lines of ethanol. Interestingly, they did this work. They wrote this up in Geneva, of all places, because Bloch had just been made director of CERN, and he said, sit down and write up your theses, and this is what they did. So we were upstaged by people writing theses in California in the same year that we were congratulating ourselves in Oxford. And it was James Arnold who built the magnet, and he did a clever thing. He built a permanent magnet, so the stability problem is much easier. And he didn't know that you couldn't make a homogeneous magnetic field to that extent, so he went ahead and did it. And he produced a magnet with a resolution of 1/2 of a hertz. Now, even today, if you get that sort of resolution, you're quite happy. So James really made a big deal on that. But I was actually more interested in this. This is an early Earthfield magnetometer being adjusted by an early version of Wes Anderson. It was Wes Anderson that attracted me, and he's one of my new heroes, as you'll realize as the talk goes on. And the experiment he did was this. He took one of his high-resolution spectra, and he irradiated this doublet, and he decoupled part of the rest of the spectrum. In fact, you can see here, this has changed its structure. Now, you're all going to say, well, okay, that's decoupling. We all know about that. It's old hat. Don't worry about it. But I want to make a very strong point here, that this was the first case at that time when you could manipulate spectra. All of spectroscopy in those days, you had your stuff, you put it in the spectrometer, and you got the spectrum, a one-to-one relationship between the two. You didn't meddle around in the spectrometer. There were no lasers in those days. So you did not manipulate spectra. I argue that this is the first case of spin manipulation, which you're all using these days, every day of your lives. Now, when you manipulate NMR spectra, you're manipulating the spins. Now, let me ask you to suspend your disbelief for just 2 minutes, if you can do that. Let's just suppose now we have this flask full of spins, and there are just as many up spins as down spins within a small correction. Supposing we pick out the down spins and take them away. This is a Gedanken experiment. You're suspending disbelief. So you have now a flask full of up spins. To do this, you need a helper called the maximal demon, and what he can do is he can put all the up spins in one flask and all the down spins in the other, and to simplify the argument, let's call them the red and the blue spins. Now we take a 3-spin system. We're going to focus on this group in the center and say we've separated that group into red and blue spins. And we take a flask of the red spins and put that into the spectrometer and record the spectrum. Don't ask what happens in the middle, but at the extremes, you see only these lines, the red lines, because those are the only spins in the spectrometer. And if you do the blue spins, you only see those lines. Now, this is actually making an assumption about the signs of the couplings to this central spin. It's assuming that they have like signs, and if they have opposite signs, you get a different picture. Now you can renew your disbelief because nobody can do that experiment. It's just Gedanken. But what you can do is to irradiate this red doublet at low field and see what happens at the other end, and lo and behold, you decouple the red spins. So this says that the 2 spins to the central nucleus have opposite signs. Now, we could have changed red and blue. It makes no difference to this argument, which means we can't measure the absolute signs of the coupling constants, but only the relative signs. You may say, as Anatole was always saying to me, so what? But at that time, Martin Karplus was postulating 2 very important theories about coupling constants. The geminal coupling constant is a function of the angle, and the vicinal coupling constant is a function of the torsional angle. And yet, both of these theories said positive couplings. And yet, we've just shown that the 2 couplings in this molecule, 2,3-dibromopropionic acid, are opposite in sign. What do? You quietly forget about geminal couplings, and many of you are still using the Karplus curves for the vicinal coupling constants, but very little is said about the geminal calculation. So this convinced me that the thing I wanted to do was to work on messing with spins, and that there was one person in the world who was going to be helpful, and that was Wes Anderson. So we had drastic measures required. Actually, Pan Am had a nice scheme which is called Fly Now, Pay Later, and we packed our little family into a plane and flew to California, where the Varian lab was, and Wes was working at Varian by that time. So this is 1961. So I want to now put you in the picture of the early 1960s. What was it like to do NMR in those days? Well, it was simple. You had continuous wave, frequency sweep, protons only, 60 megahertz. And you could go out and buy a machine that worked perfectly well. You didn't have to be an electronic expert to do NMR anymore. You could just buy a machine. And you had pre-calibrated charts. Don't ask why it's always strychnine. Had pre-calibrated charts. And it worked because they had a field frequency controller designed by Wes Anderson. Everyone was happy. You could take any chemical off the shelf, put it in an NMR spectrometer, get a spectrum, write a paper. Everyone in the world was happy. This was a golden age of small molecule NMR. You're all in it a bit too late, but that was the golden age. Everyone was happy except, can you guess, Wes Anderson. Wes said, why do we sweep? Why don't we irradiate all the spins all the time? Why don't we do this experiment where we have a whole comb of radio frequencies and we get what's called the multiplex advantage, which is the Felget advantage in infrared, or it's related to it, and we get an improvement in sensitivity as the square root of the number of channels up to the level where you have one channel per line width. You can't go on forever. So Wes loves practical gadgets. He built this machine called the prayer wheel, like the Buddhist prayer wheel, where you just, instead of saying prayers, you just swing these things, walk along. Much easier to be religious in both countries. This device has these film strips, and I won't go into details, but you can see if you change the radius of this cylinder, this lucite cylinder, in small steps, then the frequencies will gradually increase as you go down this cylinder. You pick up these frequencies on the photoelectron detector, you amplify them, and you use it to make modulation sidebands to excite the spins. Oh, this is in 1963. But let's all be careful about this. The experiment is in two parts. You have to excite the spins, as Wes was showing, with a comb of modulation sidebands, but then you have to disentangle all the results with a matching set of end detectors. And the separation of the response, Wes actually had several ideas, mechanical ideas to do this, but one which interests us at the moment is to have an array of phase-sensitive detectors. In fact, an engineer was told to go away, design a cheap phase-sensitive detector, and make a lot of them. You can see this experiment's getting clunky already. And here's Wes with, just to prove that he actually made the prayer wheel. He's smiling, but he's not happy because they're going to take this off to the Smithsonian because they never used this device. They decided, well, it was a good idea, but no, let's put it in the museum. Because Wes suddenly realized what everyone knew at the time, but only paid lip service to, was that the impulse response of any spin system contains all the frequencies. And if you have to disentangle them, you do a Fourier transform. There's actually a small prize for anyone who can read this music in the yellow thing here. But what I'm really saying is that the Fourier transformation is merely a reordering of the frequencies in the correct order. Now, it's not known widely, but this important principle was expounded first of all by an Englishman called Morecambe. And I want to show a video clip which is sure to fail because it failed this morning, but let's try it. Okay, back to reality. This is Wes's lab notebook, 3rd of June 1964. The Fourier transform resolution is here. This explains it all. This says you should be doing an NMR by Fourier transform, pulse-excited Fourier transform. I hope you can read his writing. It's not always very good, but there's a thing called a time averaging device, and he shows the pulses and the address of the time averaging device and so on. Everything is in here with one very slight problem. There weren't any Fourier transform computers. There weren't any lab computers at all. They didn't have PCs. They didn't have things in their pockets that did calculations for them. These did not exist in 1964. So there are some practical problems with this experiment. Let's look at the first one. Would FT ever be practical? Well, there's this thing called a time averaging device, or a CAT, a computer of average transients. And let me emphasize here, computer is the wrong word here. This is not a computer. This is a special purpose device which takes in free induction decays, digitizes them, and adds them together and stops. You can't do any other calculations with this device. It's a special purpose machine. It's not a computer. To get the information out, you have to put it in some permanent form, which is to punch paper tape. You then read the paper tape. You feed it to a thing called an IBM key punch, and many young girls spent their lives putting information into digital form by typing them in on an IBM key punch, a dreadful machine. And the result is a box of IBM cards and one data point on each card. So now you have a free induction decay. And now you need the second part of the experiment. You've got to do a Fourier transformation of that. And I should say this has all been done in the Wild West in California, and I'll just show you this picture. The NMR lab is at one end of Palo Alto, the IBM service bureaus at the other. You take your stuff there. They only do these trivial calculations overnight. The next morning, back comes the spectrum, with any luck. And of course, it's not in the right phase. So another overnight run, back comes the spectrum. Check the phase again, see what it's doing. You can see why they hesitated to go this way.